Hi, this is Professor Dorr, and this is Lecture 27 of EE 310, and this is our second review lecture before our final. Before I get going with the lecture today, I'd like to make a couple of comments about the course and how things have gone down this semester with the lockdown and the coronavirus. The university has given professors the option of having this semester's student ratings thrown out. So in other words, when you guys fill out your evaluations at the end of the semester, professors can have those just tossed if they wish because of the pandemic. I think that that's nonsense, and I'm opting to have the reviews that you guys write used and put in my HR file and used for, the things that HR uses those for, extending contracts and things like that. I want to be rated or recommended by the way that I chose to perform during this really difficult time. It's been challenging, but I want to be rated by this. Anything less than that would be being dishonest with myself. And personally, I would rather have a bad rating in my file than to know that I wasn't honest with myself. So that's just the way I want to do things. I encourage you all to post something on Rate My Professor. Those reviews are very important to me, and they help other students. I read them carefully. Obviously, some of them I really enjoy reading, some of them I don't, but it's important that you be honest and give other kids an idea of what they're going to get if they take my class. Okay, so let's start our review, and we'll start off with transfer functions. And we'll do a simple circuit here with an L and an R. And we want to find the transfer function, and then we want to evaluate that transfer function at 100 Hertz. And so let's look at the transfer function. We'll just use the voltage divider theorem to get that. It's going to be equal to R over R plus J omega L, or SL. This is a perfectly good transfer function right here. And as you've done on the previous exams, if I ask you to give me a transfer function and don't reduce it, this is the one you want to give me because you don't have any option for making any mathematical errors. But what I'm going to do is I'm going to put this in the form that we would use for Bode plotting. And the thing that comes to mind when I want that form for Bode plotting is I want a 1 right here. So what I have to do is just factor out that R. And what I'm going to do is really divide top and bottom by R. And I'm going to get 1 over 1 plus S over 628. 628, you'll recognize in this form, is the pole frequency for this network. So this network obviously has a single pole. And I'm going to evaluate it at 100 Hertz. And I picked that carefully because 100 Hertz corresponds to the pole frequency of 628 radians per second, because 2 pi times 100 is 628. So I substitute that in there. Here's my S, and I'm going to substitute in J2 pi F. And I end up with 628 in the numerator and 628 in the denominator. And I put that into polar form, and I get 1 over root 2, or 0.707, at an angle of minus 45 degrees. And what this kind of reiterates is that at the pole frequency, the magnitude of the transfer function is 0.707, or 3 dB down, right? 20 times the log of 0.707 is going to be minus 3, and the angle is 45 degrees, all things that we used when we made Bode plots. We introduced the tool Asymptotic Analysis, and As you saw, it's one of my favorite things because it allows me to check my work as I go. And if I make a mathematical mistake, I can often catch it with this technique. And it also gives me a really good intuitive feel about what I'm doing. And I always want that math to follow my intuition as I work through these problems. The math is my tool. So let's do it for an RC circuit. We're pretty good at getting our transfer function for the RC circuit, so I'm just stating it here. And you notice I really like to use S and J omega interchangeably. I've done that all semester. There's an S, there's a J omega, there's an S. So let's just look at our circuit and let's get the response at DC and then the response at the frequency of infinity, which is what asymptotic analysis is about. So at DC, I know that if I go back to the rules at the beginning of the semester, there's no current through a capacitor at DC or at steady state. So we can use that rule, and that says that since there's no current here and there's no current here, there's no current through this resistor, so I get no voltage drop across it. And so therefore, V out is equal to V in, and the transfer function is 1. Now, that's what we did when we started the course. We said there's no steady state DC, there's no steady state current in a capacitor, just like there's no steady state voltage across an inductor. But we can also just use the formula for the impedance of the capacitor. It's 1 over J omega C. And if omega is equal to 0, then the denominator of 1 over J omega C goes to 0, and therefore the impedance goes to infinity. If the impedance is infinity, we have no current. So we can use either of those rules, but they tell us that at DC, I'm going to have a response of 1. Now let's make our frequency infinite. And here we kind of have to use the impedance of the capacitor as our guide. We know that it's 1 over J omega C, and omega is a bazillion, and so therefore the capacitor is a short circuit. So at infinite frequency, that capacitor looks like a short, so of course there will be no voltage across it. And so at infinity, the response will be 0. So we have a 1 here, and we have a 0 here. So now let's look at the transfer function. The response at DC, we get that by just setting S equal to 0, or J 0. Doesn't really matter. We're going to set it to 0, and I have 1 over 1 plus 0 is going to give me 1. So my response at DC from the transfer function agrees with what I got from my circuit. Now let's set the frequency to infinity. And at infinity, I have 1 over a bazillion gazillion here, and so the response will go down to 0. And so again, that agrees with what I got from my circuit. So asymptotic analysis is just an excellent way to see circuits intuitively and to check your work. Here's another one. So here, our transfer function we can actually just get by inspection of the circuit using the voltage divider. It's going to be SL over R plus SL. So here's the unreduced transfer function. That's a perfectly good transfer function. So from the circuit, our response at DC is going to be 0 because I know I have no voltage across this inductor at DC, or the impedance of the inductor is J omega L, and omega is 0, so the impedance will be 0, so it'll be a short circuit. And so my response at infinity, I know that the impedance of the inductor is going to be j omega L, so that's j infinity times L, so it's going to look like an open circuit. So the response to this circuit at infinity is going to be 1. So we have a 0 and a 1. Now let's go over to our equation. And at DC, I have 0 divided by r plus 0. So I got 0 over something. That gives me 0, which matches here. At infinite hertz, this r is insignificant because my j omega term here is going to be so high, it's going to be SL over SL gives me 1. And again, that agrees with what I got from my circuit. So asymptotic analysis is a very, very useful tool. On the final, and I believe on exam 2, there are places where I asked, hey, show me that this is true. And asymptotic analysis, that's your tool. That's your tool for DC and infinity. Okay, let's move toward Bode plotting. And Bode plotting with an op-amp going on here. I believe one of the guarantees on the final this semester is you're going to see an op-amp. And so let's just look at this thing. What do I see? I see an op-amp with the positive terminal grounded and the negative terminal feeding back to the output, and then the input ends up going into the negative terminal. So really, I have a clump of stuff here, and I have a clump of stuff here. So I'm going to call this Z2 and Z1, and I recognize that I have the inverting op-amp configuration. Z2 is this clump, Z1 is this clump. And so the V out over V in is just going to be negative Z2 over Z1. Or in other words, negative this clump, which is R2 in parallel with Z of the capacitor, and divided by this clump, which is R1 in parallel with the impedance of the capacitor. So I recognize my inverting configuration. So since both of these look the same, let's just kind of work both of them in one shot and say, what's a resistor in parallel with a capacitor? You see we got a resistor in parallel with a capacitor and a resistor in parallel with a capacitor. It will be R times 1 over SC divided by R plus 1 over SC. We'll reduce that a little bit just to get stuff out of the denominator, and it's equal to R over 1 plus SCR. So now let's substitute that into our equation for VO over Vn, or our transfer function. So R2 in parallel with ZC using this formula is going to be R2 over 1 plus SCR2. And this piece of our transfer function using the same equation is R1 over 1 plus SCR1. So here's my transfer function for the circuit. Perfectly good transfer function. But we were asked to sketch a Bode plot for this circuit. So what I'm going to do is I'm going to put it in the form that I need to for a Bode plot. So what is that form? I want my 1 over here. Well, first thing I'm going to do is just get this so it's not a fraction over a fraction. And that's pretty easy. And it looks like I already have my 1 plus something. And so all I really need to do is just for this SCR2 or SCR1, I need to just put my R1C in the denominator so that I can read my zero frequency directly. So here we go. We have R2 over R1, which is our constant term. And then we have 1 plus S over 1 over R1C. So in this format, I can read my zero frequency, I can read my pole frequency. So let's do that. Minus R2 over R1, and actually since we're going to be plotting the magnitude, we'll just blow off this negative sign. And R2 over R1 is equal to 9. Our zero frequency, omega 0, is 1 over R1C, is 30.3 times 10 to the third radians per second. And our pole frequency is 1 over R2C. Now, on the exams, I insist that you place your break frequencies in the right place on the Bode plot, and you don't have log paper. And so what you have to realize is that what is going up linearly on your graph, on your x-axis, is the exponent of the frequency. So when I get my zero frequency, I get the log of that. The base 10 log gives me 4.48. Or in other words, 10 to the 4.48 is 30.3 times 10 to the third. So I take my base 10 log, and this says that on my logarithmic x-axis, I'm at 4.5 units, and that's an easy place to plot. And similarly, this one, when I take my base 10 log, I get 10 to the 3.5. So that means it's about halfway between, it's exactly halfway between 10 to the third and 10 to the fourth. On the last exam, I asked students to do this, and many of you didn't do it and didn't show that strategy. So on the final, make sure that if you're asked this, you do show this strategy. You take that log and then plot those breakpoints on the x-axis at the right place. So h of j omega, here's our formula, or our transfer function. We've got our zero, we've got our pole, we've got the log of both of those, so we know where to put them. We have our constant term. I think we're ready to go. So let's put in the constituents of our Bode plot. Our constant term is going to be 20 times the log to the base 10 of 9. This is not a negative sign here. This is just some kind of mark that came from somewhere. 20 times the log to the base 10 of 9 is 19.08 dB. That's our constant term, and it comes from here. And it's constant. It's not frequency dependent. So its contribution to our Bode plot is this 19 dB. See, I drew it just a little bit below the 20 there. Now let's take our zero. We have a flat line. The contribution from the zero is a flat line, and then above the zero frequency, it's going to fall at 20 dB per decade. And so here it is. It's 0 here, and then let's get to our zero frequency, and I'm sorry, our zero is going to go up at 20 dB per decade above omega z. So here it is, 0 dB, and then I hit omega z, which was about 4.5, good enough for me, and it goes up at 20 dB per decade. And our pole is going to be a flat line, and then it's going to start going down at negative 20 dB per decade above omega pole. So it starts off at 0, and omega pole is 10 to the 3.5, so it's clearly halfway between here, and down it goes at 20 dB per decade. How do I get these slopes right? This is just a simple little Bode plotting thing. What I do is I know it's going to go down at 20 dB per decade. So what I'm going to do is take my straight edge and go here's a decade, and here's 20 dB. And then I'm going to just lay that straight edge right here on the graticule marks. And then I'm going to keep the angle, and then I'm going to move my straight edge around. And here I just slid it over to omega p and then followed my angle down. So now I have my three terms of this Bode plot. I have the constant term at 19.08 dB. I have my zero going up here. I have my pole going down here. So now I need to just add them all up. And when I add them all up, what I do is I show the final Bode plot with a wiggler. So here's my wiggler. So for this one, I'm going to start over to the left end of the plot. And the reason I'm all the way on the left end of my plot is at the left end, everything, I have not encountered any poles or any zeros. All three terms are flat here. And I get 0 from the 0, I get 0 dB from the pole, and then I get 19 dB from my constant term. So I draw my wiggler up here at 19.08 dB, and I wiggle it away until I get to the pole frequency. And remember, I'm just adding these numbers up. And at the pole frequency, I start dropping at 20 dB per decade. And then when I get to my zero frequency, I note that my pole is still going down, but my zero starts going up. So I get a flat line here, right? Because they offset each other. And so now my wiggler is nice and flat. Now before we get away from this Bode plot, I want to make sure that you're good with why this works. Why can we add these up? At this point, you've been doing so many of these problems and you've been focusing so much on the procedure that you might be going, oh yeah, I just need to know the procedure. You know, there's some magic behind it. But go back to our first lecture on Bode plotting, and you'll see that all the theory of what we just did is really about a half a page in the notes. And it's a very simple half page. And at this point, it will really have a lot more meaning to you than when I vomited out on the first lecture there. So go back and take a look at that. And what you'll do is you'll turn rote procedure into understanding. So I really encourage you to do that. It's not going to take you a lot of time, and you'll feel good when you're done, because then you'll really understand this. You'll really command. You'll own this stuff. Okay, so we've got our Bode plot, but is it realistic? Let's take a look. Let's hit some asymptotic analysis. And so at DC, both of these capacitors look like open circuits because they don't pass any current if we use the rules from the first day of lecture, or they have infinite impedance if we just use the formula for the impedance of a capacitor. So that means they're not in the circuit. So the gain is going to be equal to -9 over 1. It's just Z2 over Z1, right? And this clump became just the resistor, and this clump just became this resistor. So the gain is going to be equal to -9. So 20 times the log to the base 10 of 9, that's 19 dB. I love it. Now let's say that the frequency is infinite. If the frequency is infinite, the impedance of these capacitors is so much lower than the impedance of these resistors that I really have Z2 equals Z1, don't I? And if Z2 equals Z1, the gain is -1, and the magnitude of the gain is 1, and therefore I'm 0 dB. Hey, that's what my Bode plot is telling me. So if I'm taking an exam and I do this problem with the Bode plot, it took me like no time to just go back and say, hey, is this reasonable? And if it's reasonable and I think I got it, I'm done worrying about this problem. I'm not even going to come back to it. I'm going to just focus on the rest of the exam. When you are working in industry, asymptotic analysis is going to allow you to look at circuits quickly. When you're in a meeting with a bunch of people and somebody flops something up in a design review, you start doing a little asymptotic analysis, you can learn a lot about it. You may be able to poke some holes in what that person is doing. So I know I keep selling asymptotic analysis. I'm not sure whether I try to sell my book more or my asymptotic analysis more, but of course, if I were to give you a commercial on my book, I would tell you that it's called 10 Essential Skills for Electrical Engineers, and it is 220 pages of what you want to know when you get out and do your interviews. This class, EE310, is about 25 pages. Control systems is about 25 pages. Digital filtering, DSP, practical digital filtering, is about 20 pages. What I've done is taken the things that people are going to expect new hires to be able to do and know, and highlighted them in here. So if you buy this book and you and after you take this class, you go through the circuit analysis chapter and you go, wow, that was really easy. And then when you take controls, go through the control systems chapter and you go, oh, that chapter is really easy. But then when you're getting ready to graduate, you look at your control theory book and go, where do I start preparing this? And then you go, wait a minute, Doerr's book did it in 20 pages, and I remember really understanding that. And then you go back to Doerr's book, and you use this to get ready for those interviews. And of course, if you let me sign your book in pen, I'll hand you $5 because that's my commission on each book. And I would much rather see this book helping you and making you better engineers and getting you good jobs than I would have that $5. So asymptotic analysis is a great tool. All right, let's move on. So let's do a little reality check. Is all this Bode plotting stuff practical? And you might notice that I mentioned that Bode plotting, a lot of people say that it's really passé, it's old school. With computer tools now, there's really no real value in it. I agree and I don't disagree. For big complex transfer functions, don't do a Bode plot, plot it in MATLAB. But for simple little things that just have a few components, like our op-amp problem here, or for this little problem, Bode plots can give you incredible insight and allow you to get information really quickly. And I've noted to you that when I had my company, and people would be presenting something, in a design review or on the blackboard or whatever, I could go through and analyze the circuits just on a napkin during the presentation, and I would often find holes in them. And I would ask the engineer, hey, this doesn't look like it's doing what you say it's going to do. And the engineer would get flustered and say, oh, well, I've got to go back and look at my simulations and look at my and I would say, no, look, just do a simple Bode plot. You can see this is not right. And that means this component is not appropriate, or this thing's going to get too hot, or whatever. But if you can poke a hole in something, the sooner you can poke a hole in it, the better for the company and the more valuable you are to the organization. So a little long-winded there, but I'm going to give you a real practical example that Bode plotting gives you the answer to. So I want to find the frequency response at this at 153 kilohertz. A typical example in industry is an engineer says, yeah, we got a little birdie at 153 kilohertz. That's what they say when there's a little signal at some frequency. It may come from a switching power supply, or it may come from an oscillator somewhere, but they say, yeah, it's a birdie. And we put this little low-pass filter in to get rid of the birdie. And I might ask, oh, well, how much attenuation do you get at the birdie frequency? Well, I don't know, we just put in this little filter. It's worked in other places. And boy, when I hear that, I smell blood. That engineer may need to go work somewhere else. So let's work this real quick. What's the response, the magnitude of the response in dB at 153 kilohertz? So the transfer function, we can work this out on a napkin really easily. And here it is. And our pole frequency is 1 over RC. Eventually, you'll just memorize this. This one I've memorized, I know it. So the pole frequency in radians per second is 1 over RC. And so the frequency of the pole is going to be 1 over 2 pi times RC. Or in other words, the frequency in hertz is going to be 1 over 2 pi times the frequency in radians per second. Because for one cycle, you go around 2 pi radians, but you only go around one cycle. So the frequency in hertz is always going to be less than the frequency in radians. And it's going to be 994.7 hertz. So how many decades are there between, or before we do it, let's get our strategy. We know that our Bode plot is going to be 0 dB at DC, because we can just see that by looking at the circuit. And we know it's going to go down 20 dB per decade above that. So really all I need to know is how many decades are there between 153 kilohertz, which is what we're asked for, and 995 hertz. That's easy. I'll do the math for you. It's 10 to the decades equals 153K divided by 995, or let's do the math. But really in the end, the number of decades is the base 10 log of one frequency divided by the other. This is something I just remember. So it's 2.19 decades. So to get the frequency response at 153 kilohertz, I'm going to start at 0, and then I'm going to go down 20 dB per decade times 2.19 decades. Here's the equation. 0 minus 20 dB per decade times 2.19 decades is minus 43.8 dB. So now I know what that rejection is. Okay, let's move on. So we want to design a series resonance circuit with a bandwidth of 20 radians per second, a center frequency of 1,000 radians per second, and we want to find Q. Now, given these requirements here, I could do this with an infinite number of components, so I need to nail one down. So I'm going to nail down R and say you got to use a 10 ohm resistor here for this series resonance circuit. And so I'm going to be like the seagull, and I'm going to go through my formulas. Let's see, the bandwidth, we know it's going to be 20 radians per second, because that was specified, and that's equal to R over L for a series resonance circuit, which is also equal to omega naught over Q. And we might remember that this is valid for any circuit, but this is valid for series resonant. And so I go through my formulas and I say, I know the bandwidth, I know the resistance, I can get the inductance, so I'm going to use these, just like the seagull does. So L is equal to R over 20. So that's going to be 10 ohms divided by my 20 radians per second is going to give me a half a Henry. So now I know my inductance. And I also know that omega naught is equal to 1 over root LC. And omega naught was specified as 1,000 radians per second. So I work through that math and I get my capacitor. So I'm also asked to find Q. So Q equals omega naught L over R for our series resonant circuit, and it's equal to 50. I just did a bunch of turning the crank, but I did nothing conceptual. And you could turn that crank and not really understand what's going on with these circuits. And as you can imagine, on the final, I want you to know what's going on in these circuits. So let's do a little more. First, let's just check ourselves. Omega naught is 1 over root LC. Okay, that's 1,000 radians per second. I'm just using the values we calculated. Bandwidth is R over L, that's 20. Q is going to be omega naught over the bandwidth. And you notice that here I used omega naught L over R. Here I used Q as omega naught over the bandwidth, because using a different formula is always good, and I got 50, and that agreed with what I had here. So now let's fire this circuit up. Let's put in an input voltage, and I'm going to ask you, what's V out over V in at omega equals omega naught? And you'll see in my practice finals, I've asked this question before. And what I don't want you to do is do all the analysis. I want you to say that what a series resonant circuit does is this impedance plus this impedance equals 0. For a resonant circuit at the resonant frequency, this impedance plus this impedance equals 0. I mean, that's where we get this formula. And so V out over V in at omega equals omega 0, when you're asked that, you say, since it's series resonant, ZC plus ZL equals 0, and so V out over V in is 1. What's Z in at omega equals omega 0? Well, if these add up to 0, I'm going to say, looking in right here for Z in, I'm going to see 10 ohms. Now we're conceptual. This is what I really want you to understand about these circuits. I also want you to understand that maximum power transfer is really the same as resonant circuits. And when you do power factor correction in EE, whatever it is, that's a resonant circuit. When you do impedance matching of RF components in your graduate courses, that's just resonant circuits. That's why this is so important. So for the series resonant circuit, we knew that V out over V in is just going to be 1, and Z in is going to just be equal to the resistance. Now, similarly, for a parallel resonant circuit, the inductor and the capacitor in parallel give you an infinite impedance at the resonant frequency. So make sure you understand that, because that's the important stuff for these resonant circuits. The turning the crank stuff here is nice, but the problems, of course, aren't going to be purely turn the crank. You got to turn the crank, but you got to know how and why to turn it. So now let's beat this thing up a little further, because what I want to do is see what happens when we move away from the resonant frequency. So let's get the current. Current is going to be V in divided by the capacitive impedance plus the inductive impedance plus the resistance. And we're going to reduce that a little bit, or rearrange it a little bit. And what I'm going to do is I'm going to plot the current divided by the current at resonance. Why do I do that? So that at resonance, this normalized value will be equal to 1. What's the current at resonance? That's easy. It's just Vn divided by 10 ohms, because remember, these add up to 0. So that gives us our yes, the current at resonance is going to be 1 over 10. Looks like we're using 1 volt here for Vn. And here is I of omega, which is just 1 over this absolute value. So here's the formula we want to plot. And I'm going to go into and use my little compute frequency response program that I've given you and posted on Blackboard a few times. And let's look at the response in the frequency domain. Remember, I'm looking at the current in the circuit divided by the current at resonance. So at the resonant frequency, of course, that comes to 0 dB. What's happening down here? Down here at low frequency, the current is very low because the inductor has such a high impedance and it's limiting the current flow. Now let's go up here. Here, the inductor and the capacitor added together give you no impedance, so you get the maximum current. Now let's go above resonance. Above resonance, the capacitor is what is limiting that current. Because the capacitor, I'm sorry, my mistake, let's back up. Down here, the capacitor is blocking the current or limiting the current because the capacitor is going to have higher impedance at lower frequencies. Here, the inductor is limiting the current. So this gives you a really good feel for a resonant circuit. What's really happening? Capacitor's limiting the current, so the current is low. Nothing's limiting the current but the resistor. Here, the inductor's limiting the current. What would it look like if we swept this circuit with a signal generator and an oscilloscope? So what we're going to do is I'm going to put my signal generator right here. It's one of the ones in the 202F lab. And its magnitude is always going to be 1 volt, but I can change its frequency. And then I'm going to look at the voltage here because the voltage here is going to be proportional to the current. So we look at the scope picture here, and at very low frequencies, when I turn that frequency knob way down, I'm going to get just a little tiny signal on my scope. But as I turn it up, that sine wave is going to get bigger and bigger. And eventually that sine wave, as I'm turning my dial, is going to go whoop, because I'm going to hit that resonant frequency. And then as I continue increasing the frequency, the magnitude's going to go down. So in other words, I turn that frequency knob up, and the envelope of my sine wave starts really small, and then it goes whoop at resonance, and then it comes back down again. So that's what it would look like in the time domain. In the frequency domain, it looks like this. The magnitude is very low down here. Magnitude is maximized here. So what let's do now is let's zoom in on this portion right here. And what I'm going to do is with my zoom, I'm going to say, and you can see I've zoomed this way, and then I'm going to zoom this way too, because I want to look at that 3 dB frequency, and 3 dB is only about right here. So I need to zoom it in. Here it is. So at 990 radians per second, check it out, I'm down 3 dB. And at 1010 radians, I am down 3 dB. Let's go back up and look at this. our bandwidth was specified to be 20 radians per second. Remember, bandwidth is our 3 dB bandwidth. Hey, look, 1010, 990. The difference between these, or the bandwidth, is 20 radians per second. And at that point, I am 3 dB down. So make sure that you understand this. Students typically do not do well on the resonance circuit problems on these exams, though they tend to be some of the, I'll say easiest, because what I mean by that is they take the least amount of computation. So if you understand the concepts behind resonance, you'll frequently find that the problems that I give you on the exam you can do them fairly quickly. I'm never going to say that anything is easy in 310. Okay, I'm going to take a break and get a cup of coffee. I would suggest you guys take a break too. We're only a little less than halfway through this lecture, and we'll continue on in a bit. Now let's move to Laplace transforms. So when we do Laplace transform problems, I really like to use the little roadmap that I made here because it shows me where we are at any time. Any problem that we do with Laplace transforms, we can put it on the roadmap and say we went from here to there, or we went from here down to there, but we can follow all our operations, and that really helps me keep everything organized. Let's work with the Laplace transform roadmap. So find the Laplace transform of a time domain function. Well, here we are, and our time domain function is here. And of course, our roadmap is organized, so it's laid out. So I have input, system, output. Or in other words, I put an input into a system and it comes out the output. And we have the time domain up here and the frequency domain down here. So find the Laplace transform of a time domain function. Here's our time domain function. We take the Laplace transform. Bella wants to say hi. Say hi to everybody, Bella. You are an internet sensation. Yes, you are. Don't scratch me. Thank you. So in our very first Laplace transforms lecture, you probably remember we went get the Laplace transform, get the Laplace transform, and we just did this over and over again. So find the transfer function of the circuit. Well, our transfer function is right here, and we learned how to get transfer functions before we even started working with Laplace transforms. We found when we got into Laplace transforms, we had this little box in the process called S-domain transfer function, and we said, ooh, I know how to do that. So another kind of problem is compute the response of a circuit to a unit step. So let's go this way. Our time domain input is a unit step. Let's take the Laplace transform of the unit step, which puts us into the frequency domain. And then we're going to take the Laplace transform of that unit step, and we're going to multiply it by the S-domain transfer function. And you're going to see we're going to get f of s, which is the Laplace transform of our input, times h of s, which is the S-domain transfer function. And now we have the response to the unit step, but it's in the frequency domain. So what we want to do now is convert it back into the time domain, and we do that with the inverse Laplace transform. And then we come out here with v out of t. Now, had we wanted, we could have taken our unit step function and we could have convolved it with the impulse response of our circuit. And that convolution would have given us the exact same answer. We could do that convolution using the convolution integral, or we could do it graphically. but the impulse response and the transfer function are related by the Laplace transform. And just to remind you one more time of why that's true, the Laplace transform of an impulse is simply 1. So that means when I multiply it by the S-domain transfer function, I just get the S-domain transfer function. So yeah, if I take the inverse Laplace transform of the S-domain transfer function, I get the impulse response. So graphically convolving the signals, x of t, and here's our little symbol for convolution, x of t and h of t. We would take our time domain signal. We called this Beethoven's Ninth Symphony a few times, and we showed that we had to time reverse it so that the first part of the symphony went through the filter first, and then we could convolve it with that impulse response. We could do it graphically, or we could do it with the integral. Another thing we did is we found the final value and the initial value of circuits from their S-domain representation. The value of this is you could look at an S-domain function and say, I know if I invert this S-domain function, or I take the inverse Laplace transform, I'm going to get the time domain output for any time I want. Because if I really invert this transfer function, I'm going to get a function of time. But what we can do is we can determine things about the time domain response from the S-domain transfer function without doing a whole lot of work. So what that means is we can get the initial value, or the value of the time domain response at t equals 0, or we can get the value of the time domain response at t equals infinity. And we do that with the initial and final value theorems. Here's the final value theorem shown for you. And so you'll find that this is very useful when you take your control systems class, because in control systems, we kind of always want to know where the time domain response ends up. So that's kind of the Laplace transform roadmap. And I like it because anything I do in this class with Laplace transforms, I can fit on this roadmap and I can see where I am. So now let's look at inverse Laplace transforms, or in other words, let's focus on this process from here up to here, inverse Laplace transform. And we have these things that I call guarantees. Book doesn't call them guarantees, it just kind of shows you how to do it, but I like calling them guarantees because the guarantee is that my first guarantee is that if I have a function that consists of simple poles, and I can have any numerator I want within physical realization, but basically for our purposes, the numerator can be anything. If I know that the denominator can be factored into a bunch of terms like this, s plus p1, s plus p2, s plus p whatever, and this p1, p2, pn are real values as opposed to complex values, then my guarantee is that I can represent this function like this, with a constant over s plus p1, a constant over s plus p2, etc. So I can break it up like this. This is the guarantee. Some smart person figured this out. And the reason this is valuable to us is that we can now use the linearity property of Laplace transforms, saying that the inverse Laplace transform of this function plus this function plus this function is the inverse Laplace transform of the big function. And furthermore, the inverse Laplace transform of these single poles is very easy. It just is A1 e to the minus P1t plus A2 e to the minus P2t, etc. So if your function consists, your frequency domain function consists of simple poles like this, you can use partial fraction techniques to get it into this format, and then your inverse Laplace transforms are trivial. Now let's say that we hit our second case. We have repeated poles, and if we have repeated poles, one of our little trapdoors in EE310 is that we're critically damped. And so f of s is equal to k of n, or just a k, divided by s plus p squared. And this could be just about any numerator. And the guarantee is that you can represent it as a1 divided by s plus p squared plus a2 divided by s plus p. And of course, if there are more simple poles here, you're just going to get more simple poles here. And you'll see that in this equation in the book. I'm just showing the critically damped part. And once we get it in this form, these inverse Laplace transforms, they're a little harder than these, but it's still easy. A1 over s plus p quantity squared is just going to be, it actually is going to refer to this one here, and I believe this A2 should be an A1. But you can see here, A2 over S plus P, that's going to be A2 e to the minus PT. And this next one is going to be A2T. It should really be A1T plus e to the minus PT. That's a little complicated because I made a mistake. But look in your inverse Laplace transform table, table 15, whatever, and you'll see the inverse Laplace transform of this and the inverse Laplace transform of this. And now we get our complex poles. And these correspond to an underdamped system. And so we recognize the complex pole condition by, we have some numerator here, divided by s squared plus as plus b. And the important thing to realize here is if you can factor this denominator into a couple of simple poles, you don't have this case. You have either this case or this case. So the way you know you're underdamped is if you can't factor this and get simple poles. Or you could also say, if the roots of this quadratic equation right here are complex, you got a complex pole. So I reminded you in class a bunch of times, when you see a denominator that's s squared plus as plus b, before you jump to the underdamped case, find the roots, because you may just be looking at a simple pole or a critically damped system with a repeated pole. Now, given these guarantees, overdamped, you can do this, critically damped, you can do this, etc. How do we get A1, A2, and A whatever? And we did it two ways. We used the residue method, which is a real clever thing, and it allows you to substitute each pole in and then calculate. And that's a pretty good method if you have simple poles. It gets a little more complicated, a lot more complicated if it's critically damped. And so I don't love the residue method. I did back when I went to college, and it was hard to solve matrices, but now I prefer to use the method of algebra because it works for this case, it works for this case, and it's going to work for this case. So I tend to use just the method of algebra for these kind of problems. And finally, for the underdamped or the complex pole, go to lecture 25 and get those formulas that we derived and use those on the exam. Have those on your cheat sheet. I don't want you to rederive that whole mess. I want you to be able to use those formulas. And I can guarantee you, if you write them down and you practice and you don't practice them, you're going to have a tough time using them. So you really have to know what you're doing when you use them. But I want you to use those. I don't want you to rederive this stuff on the exam. Okay, let's do an example. We want to find the Laplace transform of this little function here. It's kind of a funny little triangle function. And my strategy is that I see a line going up like this, and it goes between 0 and 2. And I can get the equation of that line pretty easily. And then I got another line that goes from 2 to 6. And I can get the equation of that line. It's just a little bit harder because it doesn't go through the origin. But I can break this into two Laplace transforms, because the Laplace transform of all the nothingness down here is, of course, nothing, and the Laplace transform of the nothingness up here is going to be nothing. And I can get the Laplace transform of this little piece between 0 and 2, and then I can get the Laplace transform of this piece between 2 and 6, and just add those together. So for the first segment, the equation of the line is pretty easy. It goes through 0, so the y-intercept is 0, and it goes up 10 and over 2, so that gives it a slope of 5, and I can say y equals 5x. That's easy. Second segment, I don't know about you guys, but I know it's easy to get equations of lines, but I really like a methodology of doing it. So what I do is I use the 2-point form, and that's always on Wikipedia, so I can always just go to it, because I got to be honest, I never remember it. But what it is you take 2 points, x1, y1, and x2, y2, and you say that y minus y1 is equal to y2 minus y1 over x2 minus x1 times x minus x1. And you go, that's ugly, but y is a function of x, and it's right. So I kind of suck it up, and I usually make a little table, because I got to be honest, I totally make mistakes with this kind of stuff, and I'd rather clean them up right when I make them than later, though I don't always do that. So I just substitute directly in, and then I deal with the algebra, and one step later, I'm at y equals minus 5/2 x plus 15. And I've got my equation of this line. So now let's set up the two integrals for the Laplace transform. First integral is going to be this section, and its Laplace transform is going to be the integral from 0 to 2. Hey, look at that. Bella's sitting at my feet again. She hasn't sat at my feet for like the last 3 days. It's the integral from 0 to 2 of f of t, which is 5t, here it is, times e to the minus st dt, plus my second function, which is going to be the integral from 2 to 6 of this line, minus 2.5t plus 15 times e to the minus st. So I just have to work these integrals. And this integral is going to stand by itself, and t e to the st, I know I can get that one in an integral table. Here I can split this into two integrals by just multiplying this out, and I get t e to the st again, I know how to do that, plus 15 e to the minus st, I know how to do that. So I broke it into three integrals. And these integrals are in the appendix of your textbook. And so we flop these out and we get our answer, we get our f of s. So that's how we would get the Laplace transform of this function. Now I want to do a problem that gives you an example of the Laplace transform properties. This is problem 1510 in the book. And we start off with this time domain function, and they make it as icky as they can because you're not going to find this Laplace transform in the book. So you got to use the properties. You got to break it down into simple things. So look at this mess. The derivative of t e to the minus t cosine t, and we're given g of 0 is equal to 0 because we need that initial condition as we do this problem. So the first thing let's use is the time differentiation property. And actually, before we do that, let me point out the strategy. I'm showing it just with these arrows. What we're going to do is we're going to take ugly time domain, and we are going to simplify it and simplify it and simplify it down to the smallest little function that we can take the Laplace transform of, and then we are going to apply those properties in the frequency domain. So we go simplify, 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 go to the frequency domain right here where it says Laplace. Then we're going to modify f of s based on our simplifications above, and we're going to pop out the big ugly answer to the big ugly time domain problem. It's not actually ugly, it's beautiful. So our first property we're going to use is time differentiation, which says that if I have a df dt, or in other words, the derivative of some function with respect to time, what I can do is get the Laplace transform of just the function and multiply it by s. Let me say that again. The time differentiation property says, if I recognize that I have the derivative of some function with respect to time, all I need to do to get the Laplace transform of that whole thing is just get the Laplace transform of this function and then multiply it by s. That's the property. And this is where you see we had that initial condition that was 0, so it goes to 0. So more formally, we can say that the Laplace transform of the derivative with respect to time of f of t is equal to f of s. So what I'm going to do is I'm going to say that the function that I recognize here is t e to the minus t cosine t. So at this point, and it looks like I call this g of t. Good enough. But you can see that now I have simplified it, so I'm no longer going to work with that derivative. I'm going to work with what's inside here. So I have t e to the minus t cosine t. And so what I'm going to do is I'm going to use now the frequency differentiation property, which says that if I can take what I have here, I got to get the Laplace transform of this. If I recognize this as a function of time multiplied by t, then I can say that the Laplace transform is just the Laplace transform of the thing that's multiplied by t, and then just take the derivative of it with respect to s, and that will handle that t. So what do I see? My function looks like a t times f of t, right? T, f of t. So I'm going to say, okay, I'm going to forget about the t because I can just do my differentiation later over here. I'm going to do my differentiation with respect to s later, but I really just need the Laplace transform of e to the minus t cosine t. So now again, I say, okay, the function that I'm trying to get the Laplace transform is just e to the minus t cosine t. Now, since you're all real familiar with table 15.1 because of all the homework problems you've been doing, you'd say, hey, professor, that one's in the table, but I'm going to pretend like it's not because I can use another property here. And it's called the frequency shift property. And it is if I recognize that the thing I want the Laplace transform of can be written as e to the minus t times some f of t, then I can just get the Laplace transform of the f of t, which in this case is of course going to be cosine t, and then replace the s with s plus a. So I see that I have e to the minus at f of t, e to the minus t f of t. So f of t here, we're going to call it just cosine. So now I just need the Laplace transform of the cosine. That's easy. It's just s over s squared plus 1. So now I have to do all these things that I said I was going to do up here. So first thing I will do is take my s over s squared plus 1 and replace the s with s plus a, right? So where I had s over s squared plus 1, now I have s plus 1 over s plus 1 squared plus 1. So I just did this. So now, frequency differentiation, I have to take the derivative of this with respect to s. And so when I do that, I'm not showing the steps of that differentiation, but this is the derivative of this with respect to s, as I knew I had to right here. So now the final thing I need to do is handle that derivative up here, and for that, I just multiply my Laplace transform by s. So what that means is I'll just make this an s squared. And now I have my Laplace transform of the entire time domain function. So I find that when I'm doing Laplace transforms in industry, I typically spend more time with the properties than I do the actual Laplace transforms. The tables on Wikipedia, or for me in my CRC table of mathematical formulas, which is what old people have, it's got some pretty cool Laplace transforms in it. But what I typically do is I just boil stuff down using the properties until I get something simple. So I spend a lot more time using the properties than I do Laplace transforms. Gotta be honest, I don't typically integrate, but you gotta be ready to on the final because this is EE 310. So that's our problem with the properties. We simplified f of t, follow my arrow. We took a simple Laplace transform, and then we modified f of s. Let's now look at the convolution integral. So what it does is it allows us to determine the response of a system to an excitation x of t, knowing the impulse response of the system. And of course, wow, that's a lot of words. Where are we on the Laplace transform roadmap? We got the impulse response of our function. We're going to whack it with an impulse. We're going to look at the output. And here's our convolution operation. Let's look at how we might get the impulse response. We can do it mathematically. We can have it given to us. In the example I had, they measured the impulse response of that great big beautiful church. Remember, somebody got up at the front of the church and went, and there was a psh that went through the whole church. And that was the impulse response. So they measured it empirically. And then what I did is I convolved Louis Armstrong and his trumpet through that impulse response. And we got that output waveform that convinced us that Louis' shtick wouldn't have gone over very well in the 1600s. So to measure the impulse response, we give it a whack in the time domain. I'm an engineer. A clap is a whack, and it goes through the circuit, and then I'm just going to measure the output with the oscilloscope. So, hey, here's one. Let's take a crack of lightning. It makes an impulse when that spark goes by. You get an impulse. But then it bounces off all the mountains and it goes through all the inversion layers in the air. And by the time you hear it, the thunder doesn't go pop like when you shoot a light bulb with a BB gun. It goes. Why? Because you have just witnessed the impulse response of the path between where that thunder was and your ears. And don't shoot light bulbs with BB guns. But if you do, the incandescent ones are the ones you want to use because they make a better pop. And it does sound like thunder. It's just not very quiet. Or I'm sorry, it's more quiet than thunder. So what convolution is it's the operation of taking an arbitrary input and convolving it with an impulse response and finding the output. We describe it with an integral, but I like to describe it by saying, I've got Beethoven's Ninth Symphony. It's going in here. Now let's turn it around. Let's time reverse it so that the first note goes into our filter first, and then we're going to slide Beethoven's Ninth Symphony by the impulse response, and we're going to integrate at every little piece of time. And of course, we're going to do that graphically, or we're going to do it, I do it with MATLAB. So that's what impulse response is all about. Now, another way we can get the impulse response, we just talked about measuring it, and that's a lot of fun, but we can also compute it. How do I do that? I get the S-domain transfer function for my circuit. I'm obviously not going to get it for that beautiful church, and good luck getting it from where the lightning strikes to your ear. But with a circuit, I can compute it because the impulse response, here we go. We start with an impulse. Take its Laplace transform. The Laplace transform of the impulse is just 1. Multiply it by the S-domain transfer function. That's just the S-domain transfer function. So do an inverse Laplace of your S-domain transfer function, and you got your impulse response. Here's an example, our little RC circuit. Here's the transfer function. The inverse Laplace transform of the transfer function is this function right here, 1 over RC, e to the minus t over RC. It's the impulse response, the RC circuit. Now, formally, we use the convolution integral, and we can express it 2 ways because these are commutative. If we have 2 functions, x and h, we can express it as the integral of x of lambda times h of t minus lambda, where lambda is a dummy variable and it integrates out, thereby leaving us a function of time. Or we can switch these around so we can have h of lambda times x of t minus lambda. And this integral is represented by this special operator for convolution. And this integral, I like to put some intuitive insight behind it. So let's look at time reversing and shifting functions, because everybody thinks that we ought to be good at this and we ought to know how to do this, but I got to be honest, I get messed up on this all the time. And I'm going to show you the little way that kind of helps me. And I got to be honest again, I end up doing this every time I end up with one of these. So say we know what x of t looks like. We want to know what x of t minus lambda looks like on the lambda axis. Why am I interested in this? Because we're going to integrate on the lambda axis, and we have our x of t minus lambda, which is one of the constituents of our integral. So what I showed you in class is that here's our function x, and I'm just going to say x of dot, because it's a function of whatever is inside the parentheses. So x of 0, put a 0 in the parenthesis. And remember, this is our dot axis here, right? If dot is 0, we're 0. If dot is 0.5, we're 0.5. If dot is 1, we're 1. X is a function of whatever is in the parentheses. So now what I'm going to do is plot x of minus lambda on the lambda axis. And so if lambda is equal to 0, then x of minus lambda is going to be x of 0. It's going to be 0. Now I'm going to make lambda equal to negative 0.5. So that means I'm looking at this point on this axis. And that means x of minus lambda is going to be x of negative 0.5. And that means x of 0.5 and x of 0.5 is right here. Because what is in the parentheses is 0.5. What is in the parentheses is 0.5, because we're looking at x of minus lambda, and here's my point. And by then I can see where it's going, and I know that x of negative 1 is going to be 1. So here's time reversing. Now what let's do is let's plot not just x of minus lambda, but x of t minus lambda on the lambda axis. So I'm going to set t equal to 2, and I'm going to plot x of 2 minus lambda. So lambda of 2, or in other words, I want this point. So lambda is 2. So my dot, or the thing in the parentheses, is my 2 minus 2 is 0. So that means the thing in the parentheses is 0. And x of 0 was 0. So here we are at lambda equals 2. Now let's do lambda equals 1.5. The dot is going to be equal to 2, that's this 2 right here, minus 1.5 is equal to a half. And x of 1/2 equals a half. So at 1.5 we put our half. And now we're starting to see how the movie plays out here. And we can see that adding this t in here moved our function over to the right by 2 units, didn't it? Here's x of minus lambda. Here is x of 2 minus lambda. So given x of t, we want to place x of t minus lambda on the lambda axis. So draw the lambda axis, mirror image your function x, and then shift the mirror image right t units. And that is what you're doing in this integral right here. Now, the way I like to interpret this is h of lambda is the impulse response of the circuit. X of t minus lambda is where Beethoven's Ninth Symphony is at this particular instant of time. So here's your impulse response, and the Ninth Symphony is bang, here at t equals 17 seconds. Integrate the whole mess, you get your output. Now move it to the next t, integrate the whole mess. But you see how the symphony is sliding through the filter. And that's not just convenient to help me understand it. That's how FIR digital filters work. And I hope you've picked up some of that insight in this class, because then when you get to your DSP class, or you get to the section on finite impulse response filtering in my book, it will really help you. And my book presents it this way. So I really demystify digital filtering, FIR filtering. By the way, that's this book right here. And if we look right here, we go to the chapter on digital filtering, and there it is. There's the lambda axis, and here is your discrete integration. I should also notice that the last chapter of this book is called Getting a Job, Keeping a Job, and Enjoying Your Work. And when I wrote the book, I wanted it to be only technical. I figured there was enough nonsense about interviewing and how to get a job and how to survive an interview and all that kind of junk. There was plenty of that, but there wasn't good technical material. But everybody I had worked with said, you know, you love your work so much, and you have for years and years and years. Can't you write some of that down? So I reluctantly wrote that last chapter, and it's the most popular chapter of the book. It's really helped a lot of people get jobs and given them really good insight about what to expect when you get to your job. So that wasn't a commercial. That was all part of the example, because I just wanted to show you that lambda axis. But it was really a commercial. So buy the book and bring it to me. Let me sign it, and I'll give you $5, or maybe I'll buy you a cup of coffee. I just want you to have the book because I want you to do well. Okay, so we've gone over this whole shifting and time reversing, and this isn't easy stuff. Beethoven's Ninth Symphony is a lot easier, and it's a beautiful symphony too. Let's do a graphical convolution, because we can, if we just slide one function past another, we can actually see it graphically, and sometimes by seeing it graphically, the math is really going to pop right out in front of us. So that's what we're going to do in this example. So I have these two functions, f1 and f2. And what I want to do first is I want to ascribe some practicality into this problem, because I want to make it intuitive. This is the impulse response of my filter. I'm going to say that F2 is the impulse response of my filter. Let's go back and make sure we're cool knowing what that means. So here's my filter and my impulse response. If I put this impulse response in to the input, instead of getting this little boingy here, I'm actually going to get a up, hold for a bit, down. See that? Instead of getting this, my impulse response, or what the output does when I put an impulse in, is I'm going to go, and what's going to come out is up, down. That's the impulse response of this rascal. So here's my impulse response, and here is the signal that I want to use as my input. So what I'm going to do is I want this signal to go through that filter. Let's just look again. I want to slide that input past this impulse response. But of course I want the part of that input at t equals 0 to go in first. That's the time reversal. So let's say we want to put Beethoven's Ninth Symphony through here. Then I don't want to put the last note in first. I want to put the first note in first. So I'm going to turn it around. So we want to put this signal through. So what we're going to do is I'm going to time reverse it. And look how now I've made this my lambda axis, completely consistent with the integral. So what I'm going to do is I'm just going to slide my time reverse signal past that filter impulse response. And so the nose of this function is going to be t equals 0. So when I'm at t equals 0, is there any overlap between these functions? Absolutely not. So let's make our final answer, which is my wiggler. Let's say as this function slides, remember the value of t of our output is going to be the integral of this times this. But when t is equal to 0, then this function is over here. There's no overlap. And I can slide it up to 2, and there's going to be no overlap. So my result is that I get no overlap, meaning I get a 0 output up until 2, t equals 2. Now at t equals 2, the nose of the function begins to overlap with the impulse response. And so I'm starting to get some shared area. See this little shared area in this little triangle here? So it started with nothing when the nose was at 2. Here's my output. Yep. And as I slide that triangle in, the shared area gets greater. So now I'm going to go to t equals 3, or the nose of the triangle is at 3. And so now my triangle is completely inside my impulse response, so the output's just going to be the area of the triangle. And it's going to continue to be the area of the triangle until t equals 5, because that's when we're going to start reducing the shared area. So over here you can see that when we got to 2, we started picking up area, and then when we got to 3, the area stayed constant, and it was 1/2 base times height, which is going to be 1/2 times the base, that's 1 times the height, which is 1/2. And I know that I am at 1/2 here. And now, as t goes beyond 5, the shared area is going to get smaller. And so that means this output is going to go down. And by the time I get to 6, there's going to be no overlap at all. And I'm going to be back down to 0. So this is just my seat of the pants graphical convolution of these. And also, you can say that this is the output I get if I feed that triangle signal into that circuit that had the little impulse response that looked like this. And next, we're going to do the math. So we've done this problem by doing it graphically, and that gave us really good insight where we could see what happened when we slid our little triangle through this little rectangular impulse response. But now let's do it mathematically. So first of all, we know that below t equals 2, there is no response, because we saw up here that below t equals 2, there was no overlap whatsoever. So we can say that for t less than 2, we know that the response is going to be 0. Now let's do our next little section. And this section is going to be where we begin to get overlap. And so it's going to be the section from t equals 2, which is where we start picking up area, to t equals 3, which is where we are fully inside that impulse response. And so our integral, our lower limit is going to be 2, because you can see that as you slide the triangle, that lower limit is going to stay right where it is. So our lower limit of this integration is 2. And our upper limit of integration is where the nose of the triangle is, which is t. So we're going to integrate from 2 to t of t minus lambda d lambda, and that is going to give us t squared over 2 minus 2t plus 2, and I showed the math here, but basically this is our formula for time between 2 and 3. So let's do a sanity check. F of 2, or in other words, we know that at 2, the answer better be 0. So if f is equal to 2, I have 4 over 2, that's 2, minus 4 plus 2 gives me 0. Good. And I know that at time equals 3, the triangle is completely inside that impulse response. So the output is going to just be the area of the triangle, which we computed before to be 1/2. So I substitute 3 in there, and here are my little numbers that show that, and I get a result of 1/2, and that is good. So I've got a good definition of the function from 0 to 2, which was 0, from 2 to 3, it's this function. Now let's look at our next region. In this region, well, first of all, between 3 and 5, t equals 3 and t equals 5, the triangle is completely inside my impulse response. So I'm going to get a constant output because that area is going to be constant no matter where it is in here, and it's just going to be 1/2. So the next region begins at t equals 5, or in other words, when the nose of my little sliding triangle hits the 5. And in this region, my lower limit of integration is going to be t minus 1, because the lower limit is going to be 1 unit below t on the lambda axis. So here's my lower limit, and my upper limit is 5. And you can see this is the opposite of what we had here. Here, the upper limit was changing with t, and the lower limit was staying constant. But here, the lower limit is changing, and the upper limit is staying constant. So again, we have our t minus lambda dt, and we work through all that, and we get this function here. Now our sanity check is going to say that if t is equal to 5, or f of 5 is going to be 1/2, because that's the very last point where the triangle is completely inside, or in other words, its little nose is right here at 5. And f of 6 better be 0, because when its nose is here, there will be no more overlap, so it better be 0, and our sanity check works out. So we can plot it, and look at the Excel plot that I gave you. Excel is wonderful for doing these kinds of things, because remember, our f of t, or our output, it had one function here, another function from 2 to 3, a constant from 3 to 5, and then another function from 5 to 6, and a final function of above 6. And Excel does that beautifully. And if you go to this Excel function, or this Excel worksheet that I posted, you'll see that. And it's kind of a cool looking picture. Okay, so now let's move to Laplace transform applications. And we have our we're going to use the same functions we used last time. And I want to give you some more insight into the convolution integral. Really, what I'm going to do is I'm going to set it up like a digital FIR filter, and hopefully that'll give you better intuition. So here's x of t and here's h of t, and we're pretty familiar with those. And we know that we had to time reverse x of t, so we could put the first note of this music through the filter first, or earlier in time goes through the filter first. But what I'm going to do now is I'm going to do the integration as a discrete calculation. I'll do it as a sum. And you remember the Riemann sums that you worked with in calculus, and you made the little time integral smaller and smaller and smaller, and then out popped the fundamental theorem of calculus. Talk about smart people. Yeah, there's smart people there. But I'm just going to represent the integral using a sum. So here is I'm going to call this my lambda axis. And I'm going to divide it into little periods of tau. And this looks like a shift register, right? Because if I put the triangle in, it's going to get delayed, and then it's going to come here, and you're going to see it slide through this thing because of these time delays, right? It's like a little bucket brigade passing it through. But what's going to sit still? This thing sits still. So I'm going to represent it as a bunch of what we call tap weights. So basically, we're going to have a bunch of zeros. We don't have to put those here, right? Because it's just multiplying by 0. And we're going to have a bunch of zeros here. And that's going to give us all the zeros out here. We don't need to include those. But here is my discrete representation of h of t. Now, in this case, h of t is a constant all the way across here. So these h values would all be the same. In the case of that big, beautiful church, those h values would be the impulse response of the church. Or in other words, they would be the, and obviously this would be very long. And this would be maybe 0, and then these would start going up. I'm plotting the h's, right? And then it'd go down, and then it'd go up. And so I'd get this great big long impulse response. And that's the discrete representation of h of t. And now we are multiplying that impulse response by what we see in our shift register here, or our bucket brigade. And at each point, like we freeze our triangle at one point here, the integration is just adding all this stuff up, just like a Riemann sum. So the shift register is the lambda axis. H of t, or the impulse response, we just have a discrete representation of it. And then we just add these up, because after all, we're integrating, and we get the output. And what do we have here? We have a digital filter. And that digital filter, my bucket brigade of taus, that's a digital shift register. Of course, it's multi-bit. It might be an 8-bit values going here, and maybe 8-bit values here, but it's just this thing. And that's how I develop it in the book. Not that this is a commercial for the book or anything like that, but I sure do hope that you'll get the book. But I like this view of convolution best because it puts it in terms of digital filtering, and now I can see it. I can see the music going through all these memory locations. And with each tick of the clock, it gets shifted through this 8 or 12 or 20-bit shift register, then multiplied. And that's exactly what the operations in a digital signal processor do. Okay, so now let's move into an S-domain thuds and boings kind of problem. So we want to find V of t. Here's V of t, here's the plus, here's the minus. I didn't really have to put the plus and the minus because notationally, if I say find V of t, the implication is that it's just V of t to ground. So what we want, let's just look at it first. So what do we have? We have a switch that's initially open, and we have a voltage source. And let's see, this switch is open, so what do I have? I have no voltage across this inductor. I have no current through this capacitor because the steady state current through the capacitor is 0. So let's see. At t equals 0 minus, I'm going to have this voltage source goes through here, no voltage here, and then here's the return path, right? Because I got nothing here because there's no DC. So I really see a voltage divider with a 1 ohm resistor and a 2 ohm resistor. Because of course I have no voltage across here. Some of you like to draw it as a short circuit. I just remember the rules and I know I have no voltage here. So if I were to look at the voltage here, which would be the same as the voltage here, it'd just be a voltage divider. 1 divided by 1 plus 2 is going to be 1/3 times 12. I'm going to have 4 volts here, and I'm going to have 4 volts here. So cool. I've got 4 volts across the capacitor. That's my initial condition. And now I also have some current through the inductor. What's it going to be? 12 divided by 2 plus 1, that's 12 divided by 3. I got negative 4 amps, the way I've defined I sub t here. So it's going to be a fun one because we got to deal with the initial conditions here and we got to deal with the initial conditions here. Just a quick note about initial conditions. Initial conditions relate to energy in the component. And for the capacitor, the energy is 1/2 CV squared, or in other words, energy is related to the voltage across the capacitor. For the inductor, energy is 1/2 Li squared, so the energy is related to the current through the inductor. So when we talk about initial conditions, for the capacitor, it's the voltage. For the inductor, it's the current. So now we're cool with this circuit. We know what it's doing. So we want to draw an S-domain schematic with the initial conditions. Typical thing for a exam or a homework problem. Redraw the circuit in the frequency domain and make sure you represent those initial conditions. Here are our initial conditions. We just calculated those. We got negative 4 amps in the inductor, and we have 4 volts across the capacitor. Notice I said voltage across the 1 ohm resistor, but that's the same voltage as across the capacitor. So now I'm going to go to the beginning of the lecture where we talked about, I forget which number it is, but we talked about Laplace transform applications. And you see that I'm redrawing the circuit. The resistor stays the same. The inductor, it's 1 Henry, so SL is equal to just S. The capacitor, the impedance is going to be 1 over SC. So when things get in the right place upstairs and downstairs, we end up with 4 over S. But now let's get those initial conditions in there. So at t equals 0 plus, this is a short. So the little fanny of this inductor is going right to ground, but we got to include that voltage source for the initial condition. And the voltage source that we're going to use is L times I of 0, and that is going to be -4 volts. It's weird. An initial current turns into a voltage. There's nothing magic about that. Just go back to the first couple of pages of that lecture or the first few pages of chapter 16. It's really cool. Now let's handle the initial condition for the capacitor. We had, sorry about that. We had 4 volts across the capacitor, and so when we show those initial conditions, we have our just VO over S, or the initial voltage across the capacitor divided by S, just like it shows in that lecture and in the book. And here is our S domain circuit. Take a good look at this circuit, because if you're asked on the final to convert a circuit into the S domain, this is your guy right here. So what I need to do now is come up with V of S. We want V of T. That's what we're asked for, right? But we're doing this the Laplace transform way. So we want to get V of S, and then we will invert that. We'll take the inverse Laplace transform and get V of T. So what do? I'm going to be the seagull here and say, I guess I can write a current equation at this node. So here's my V. So I got V over 1, yeah, that's good, plus V minus 4 divided by S, divided by, sorry about that, yeah, V minus 4, and look at these signs carefully, because if this was plus to minus 4, it would just be V minus 4, but what it really is, there's a -4 here, and the polarity is turned around. So don't let this mess you up. You can tell it messed me up about 20 seconds ago, but it's not messing me up anymore. So here's my second constituent of my KCL equation. My third constituent is going to be V minus 4 over S divided by 4 over S equals 0. So the seagull wrote that equation and says, what do I got? Looks like I got one equation in one unknown. That's a good thing. I just got to solve this rascal for V. So I do all the solving kind of stuff, and I write things out, and I use common denominators, and I use all that stuff, and it's so easy when it's all laid out here, and it's so hard to do it on an exam, and I totally get that. But by the time I'm done, I end up with V equals 4 times quantity S plus 4 divided by S plus 2 squared. And this is the end of the lecture notes, but let's just take a look at this. What's the next step? Next step for me is to take a walk because it's a beautiful evening outside. But in all seriousness, I look at the denominator here because I need to know which of my guarantees I'm going to use for my partial fractions. And what I see is 2 repeated poles, S plus 2 times S plus 2. So what I'm going to do is I'm going to go up to my guarantees. Here are my guarantees. Is it this one? They're simple poles. Nope, these are different. Repeated poles. Here's our animal. It's critically damped. So here's my guarantee. I'm going to take that, and I know that I can represent it this way, and then I'm going to use the method of algebra to get my A1 and A2, And remember here, I had my A1 and A2s mixed up from here. But from there, I'm going to use the method of algebra, get those that A1 and A2, and then I have these trivial Laplace transforms, and now I have v of t. Before we leave this problem, inverting this will give us v for any t we want. What if, once you had got this equation, I said, what is going to be v of infinity? Do it any way you want. You could do a couple of things. You could use the final value theorem. Sorry, you get it to here. You could use the final value theorem. You just have to multiply this by s and take the limit as s goes to 0. Final value theorem's weird because the value at t equals 0 is going to come from substituting s equal to infinity. Well, time and frequency are inversely related. That's another of the trapdoors that I love so much about EE310. Bottom line, you want to know this value at time equals infinity? Use the final value theorem. And come here. Oh, come here, you rotten cat. Come here. Come here. Bella, I want you to say goodbye to all my EE310 students. I want you to wish them all the best of success in the final and wish them the most wonderful summer they can possibly have. Tell them I'll miss them all and that I want them all to come into my office and stop me in the halls and say hi and remind me that they were in my 310 class. Can you do that for me? Well, she tried. Okay, so you were asked to get the final value at t equals infinity, and you can use the final value theorem. There's another way to do it. Let's go back up here. What's the value of 0 at time equals infinity? Let's see. We are going to close this switch. And so let's just look at this thing at t equals infinity the chapter 8 way. The voltage here is going to be 0, right? Because this is shorted. At steady state, or time equals infinity, there's no voltage across the inductor, so if this is 0, that's 0. Quick enough. Asymptotic analysis got you the answer. So you could do it that way too. All right, folks, that was EE310. I sure wish we didn't have this shut down because one of my favorite things to do in the world is to teach you guys this material and share it with you, share my enjoyment, just the joy I get from this material. As the class is wrapping up, I know you've got to worry about the final and you've got to worry about all your other finals and everything like that. But when the dust settles a little bit, think about whether you like this stuff. Like, if you forget about all the stress of going through a really difficult class, did you really like getting the answers to these problems? Were you turned on by the transmission towers? I had one student in the class who went off-roading with all his buddies, and they found a bunch of transmission towers, and he sat there in their Jeeps and explained to all his friends how the transformers worked and how the power was distributed to your home. He was just digging it. So if you really enjoy this material, listen to that itch. Maybe think about doing a senior project in this area. Maybe think about going into analog IC design. So, you know, you may enjoy it as much as I do. But also remember that these are the fundamentals of signal processing. This is why I always ask Dr. Me if I can teach this class. Unfortunately, he generally lets me teach it because these are the basics of signal processing. When you've done it for a while, you will find that you don't care whether it's analog signal processing like this or it's digital signal processing. There's really no difference. All the transforms all do the same stuff. And as you're working in industry, you'll be able to parse problems out. You'll say, oh, we'll do this with analog electronics, we'll do this with digital electronics. And for me at this point, it just doesn't make a difference. I love it all. So anyway, I'm going to just repeat it one more time because I'm really serious about this. I want you guys to stop me in the hall when you get back. I may not recognize all your faces, but I want to know that you are in my class. My class comes with a guarantee. If you need help with this material, come to my office hour, come to my office, E410, and I'll be glad to explain it to you. So everybody do well on the final. I'll see y'all in better times.